Dear participants, very good morning all. We welcome you all on behalf of Sri Krishna College of Engineering and Technology and Department of Computer Science Engineering to ATAL sponsored online FDP on Intelligent Computing in Data Science, Day 5 and Session 12. Today, today's topic is Computer Vision on Data Science. It's for Session 12. It's a great pleasure for me to introduce our resource person, Mr. Jude Alphonse, RPA Developer, KAAR Technologies, Chennai. It's my privilege to share his notable achievements. He had conducted various trainings and handled various sessions on computer vision, machine learning, natural language processing, deep learning, and robotic process automation. Our guest is certified with various skills such as Python, Automation Anywhere Certified, Advanced RPA Professional, Bot Developer, Deploy Machine Learning and NLP models with Docker. He also honored with Special Innovator Award for the work Smart Mirror with Alexa. It's our great privilege to have you as resource person for our ATAL FDP, sir. Thank you for accepting our request. Sir, kindly take over the session. Over to you, sir.
Okay, thank you so much, Atal. Good morning, all. I'm Jude Savio, and it's wonderful to meet you all here in this very fine morning. So, without any further ado, I'll just start sharing my screen and let's jump into the session right now. I hope my screen is visible to everyone. Can someone acknowledge, please?
Yes, visible.
Okay, thank you. Okay, hello all. So the topic I'm taken up today to share with you all is computer vision in data science. And with this presentation here, I would the aim of my presentation here is to provide you with an idea about how computer vision is making a great impact in data science and in our lives as well. A brief introduction to neural networks and some of its applications, and how CV can be, you know, essential, play a key role in saving people's lives as well. And in the end, it will be followed by a demo which, out of my own interest, I had developed being in this field of RPA, which is robotic process automation. So as mentioned earlier, I'm Jude Savio. I'm currently working as an RPA developer in KAAR Technologies for the past 1.5 years. I own expertise in process discovery for RPA, constructing AI ML pipelines and doing research, which is basically R&D. I also am specialized in system landscape analysis of the customer side. So we go on and we play. I'm sorry. Okay, so sorry for that. We also, play around in the customer's landscape to how to get a sense of how to deploy our solutions, our bots, or even our machine learning models there in their landscape as well. And finally, we do engage in process automation and design thinking of our bots as well. So you can feel free to connect with me through the three platforms on the bottom right corner, which is GitHub, LinkedIn, and Dev. So you can just search me with the same name, Jude Savio, and I'll just show up in your first search query. Yeah. So let's begin with our topic today. So how I got into computer vision. So this is just a small story from my life when I was in my college years. So me and my friends, we had gone to this particular technical exhibition. Okay, so this is quite a big deal for us back in the day. since we got invited to attend this session, where people from that time, they used a lot of new age technologies like VR, blockchain, artificial intelligence, machine learning, and everything, and they incorporated it into very tiny, teensy, very small dimensions of packages and presented us in the name of projects. So we even met a small girl there. So I believe she was in her sixth standard, and I still believe she must be in her school. She hasn't even completed her school yet. She did this project called Brain Car. Okay, so during showcasing, she literally wore a helmet with a single wire, and with the help of that helmet, she controlled the circuitry of a remote control car. And just by thinking, she made the car move. She made it move forward, she made it move back, but she only could do those two operations. But still, we were taken aback by this demonstration at first, and we didn't really think that this girl was able to do everything. And upon further questioning, she had everything figured out. She could even beautifully articulate her business plans, to the extent she started pulling out graphs and depicting the percentage of increase in users with this model fitted inside their car. So the first thing we got to saw in that exhibition was pretty insane. So we knew that we were definitely in the wrong place there, because we weren't as much as rooted in the field like we were back in now. We are here now. So because we did not, but this is not the reason we got pulled into computer vision. The following one did. So what happened was, when we went into this exhibition, right? So we missed out to get registered with the front desk. So we had only done our online entries and not received our tags. So we were called out by the security, and we were asked to register ourselves. And we go to this guy on the front desk, and without any papers, any pen. He just asked us for our ID cards and the unique number which got generated when we were registering for the event online. And within a matter of seconds, he used no pen, no paper, just a camera, instant print of details in a beautifully printed format, and he handed over to us a beautiful tag and with a rope around it. It just took us 2 minutes max for literally four people. And you know how things start getting messy right from the registration, right? When people come in, they form huge queues, there's chaos everywhere, but they beautifully managed it. So we realized it on the spot. It was not an ordinary task as I say it is, because if you didn't notice, people come with different ID cards which are in different formats, right? It can be of different design, you can have different logos, you can have different fonts of texts and whatnot. Yet he was able to beautifully consolidate those information, extract those, manage those data, and print them in a template in an effortless fashion. So that is our first ever interaction with the term computer vision, but we ourselves didn't know it was computer vision back then. So we also went on forward to see a lot of stuff there, different applications of computer vision, such as tactical drones, land rovers that could identify targets, warehouse management solutions, security solutions, and more. So that was the starting point and the gentle push we needed to get into this particular field. So why I like CV? So I've articulated 4 points here depicting my passion towards CV, which is because it is basically dynamic in nature. You train it once, it is able to identify beautifully the ones which it has not seen. Sorry, and it has countless real world applications, if you ask me. And there's a worldwide support both in terms of hardware, software, and everything. And there is also countless models of delivery. It can be hardware, it can be software, it can be onboard, it can be on the cloud, it can be a hybrid solution and whatnot. So moving on, this will be the agenda of our presentation today. So you'll be taken across through a brief intro to computer vision, some beautiful examples and applications, frameworks and algorithms which I usually use, and the others out there as well, and followed by a demo. So let me reiterate again, the purpose of this presentation is to shed some light on the possible applications of CV. And what I've not covered here is that the whole domain of modeling, maintaining, retraining, and whatnot, because that can take a separate presentation, separate time as well. So that is a huge topic to cover, and I didn't want to dive into that in my current session itself. So moving on, let us see what CV basically is. Let us see what textbook definition of CV is. So computer vision is an interdisciplinary scientific field. So it basically deals with how computers can gain high level understanding from digital images or videos, basically from pixels. From the perspective of engineering, it seeks to understand and automate the tasks that the human visual system can do. So this is where RPA also pitches in, my field of work pitches in. So just imagine a company where thousands of employees work. They receive a lot of documents in their company, right? Or some documents like invoices, bills, memos, status updates, and whatnot, right? And they also do regular monotonous stuff. So they see all these documents, they see the data written inside those documents, they take it out, they put it in their systems, and they do this day to day, right? So that is what we try to make with the systems actually. And in the late 1960s, if you see, computer vision only began at universities which were pioneering artificial intelligence, and it was meant to mimic the human visual system. And as a stepping stone to giving robots this intelligence, in 1996 it was believed that it could be achieved through a summer project by attaching a camera and having it describe what it saw. So this is where it all began. So this is the starting step. Everyone does these days when they get into CV. So that is how it rolls nowadays. So CV is quite underrated if you ask me. Not many people get into CV the first try because of the very complex topics, the types of algorithms out there. People usually get intimidated, or they do not find the passion as they have towards the statistical models of regression or data exploration or whatnot. So many people believe they to get started in CV there is a large amount of investment required in terms of equipments, in terms of cameras and sensors. But that is not the case, and in terms of software as well, but that is not the case usually. And additional software and service purchases are also required to facilitate completion of even a small proof of concept, which is also not true, because there is a lot of third-party open source solutions which you can register for a free trial account, and you can start using their tenant for hosting your solutions, creating your own models as well. They also believe that there is a lack of well-defined thorough materials which deals in depth about the topics they wish to explore. So they would have picked up a particular topic and they would not have found any material. But that's not how CV works here. And programming language boundaries and lack of not knowing them. So some might know Python, some might know C++, some might know JavaScript. But the truth is, the CV aspect of things, the truth is you can do it in all these three languages basically. And finally, the lack of people concentrating deeply on this particular niche and shortage in engineering application problems in CV. So not many people get started in CV is basically the whole point of this slide. So I'm just here to prove it wrong actually. So what do you find the most common use of CV these days? Many people have these and yet they still don't recognize the value here. You can see people on the roads, you can see people having it all the time in their hands. You can see people getting lost in a world of their own. So if you haven't figured it out yet, it is actually the facial unlock you see on smartphones, right? Right, from iPhone to OnePlus, all phones nowadays come with this facial unlock, which deals with certain data points on your face. It projects dots, especially in case of iPhone. They use an IR dot projector to basically scan the bone structure of your face. So they take data as deep as that. That is why they are able to, even if you initially register on the phone with a full clean shave, you're on a clean shave, you do not have a single piece of hair on your face. You grow a full beard in 3 months and you come like a caveman, and yet the phone is able to still recognize you. So that is how they have structured their algorithms inside there. So moving on, let's also see the other major examples of computer vision. Excuse me. One of the huge players in the market that that has incorporated CV into their products is Tesla. You might we all know they've enabled this automated co-pilot in their cars. They also have autopilot mode in their vehicles during based on different road types. By road types I mean on highways, on suburbs, on cities, etc. Warehouse management applications like uh, boxes that come on a vendor belt, right? So they can be with defects, they could be with crevices, they could be with certain scratches or something, and that might get the box rejected. But if it is not looked at properly, it can result in a very unhappy customer, right? So cases like that, or if you want to check if there's space on your inventory, you could use CV there as well. Security, and one such thing in terms of security I found recently is that I read this article actually. So there's this case where they used it to detect robberies. Okay, so I believe it was a shop actually. I believe it was a shop or it was a company. I'm not sure. What happened was one of the employees, they what they incorporated was not facial detection alone, but also body movements. So they tracked all their body movements, and they've also added features to detect any weaponry. So that is what happened. So when the employee started showing signs of violence, when he was trying to get violent, he took out his knife actually. So the camera was initially able to pick it up and give a red flag there then and there, so that the security could act upon it. So they were able to apprehend that particular employee in their company before he could do any real damage to the others. So that is how security is evolving slowly and slowly to greater extent. So recent addition will be tolls and traffic lights, where you get parking tickets based of traffic light signals, and cars get scanned on tolls. But that is barcode. But in some countries they are enabling CV as well to detect the person sitting inside, his state of mind, and if he's under the influence of alcohol or whatnot. Remote surgery as well. The recent application being their doctor from London conducted his surgery from London to his patient who was in US, I believe. And data management. The previous case which I explained earlier, wherein companies receive a huge amount of documents. They do this on a daily basis. They dedicate personnel to do only this repetitive task each day, and not allowing them to do any other value added task that might prove profitable for the company. So that is where CV can pitch in here as well. So let us see some moments where CV actually helped save people's lives. So this is basically a compilation of Tesla's accident detection. So if you can see, before even the human mind processes that information, it is able to act upon it. So that is how the next clip would be even more surprising to you guys. See, if you could see the car on the left, it hit that truck, but we wouldn't have been able to react to that exact moment there in that speed, right? So that is how CV is here. So I'll just allow you guys to watch in peace the rest of the video. So this is completely autopilot mode. This is completely autopilot mode, not the person driving the car. So this basically detects, the road lines, the lines on the road, the course of the cars, the course of the other cars going in front and back and everything. So that is why it is able to make that decision. But it does not see things like we see. We see colors here. We see people standing on the side of the road. We see cars. We see the tarmac conditions, if it is wet or whatnot. But what it sees is just pixels. So that is why it is able to act upon it even sooner, because it has been trained on a pixel level. So this is yet another moment. This is a recent achievement during our pandemic times. This is from April 2020. Actually, there was this guy from an university who had achieved nearly 98 percentage of accuracy just by seeing X-rays. He built a model that could discern if a person has COVID or not. So this has been put into even greater extent of research by even bigger tech giants, and they are planning to make commercialize this and open source it, so that there is a lot more contributions coming into this particular idea. So you can also refer this paper at this particular URL I've given. So just head on over to it when you get the time after this presentation. So let's start talking about the main player who enables us all to get started with computer vision. So basically he's Python. We all know Python is the world's most dynamic programming language when it comes to the top ranking programming languages, and it's basically a daily driver for me. Even when it comes to creating RPA bots, I use Python. Even when it comes to creating my model pipelines, I use Python. There's always a role for Python to play, be it data handling, be it image exploitation, be it ordering those images, being labeling those images, and finally even microservices and model serving. You create the model, you host it somewhere, you open source its APIs, right? You open its APIs to the online world. So that is where Python comes with an end-to-end involvement when it comes to these things. And it also has a number of predefined libraries and packages that reduces development times significantly. So I'll be discussing an architecture of neural network later in the coming slides. So so basically from the previous sessions you should have this idea that you can create your own architectures for neural networks basically. So even if you're not able to do one, basically the packages that come within these libraries in Python, they come with a standard architecture where you just have to change the number of neurons, you just have to change the number of layers and whatnot, and still it will work. And it also has a lot of open source and well-defined guidelines, so you have very good documentation out there. Just by reading documentations you can get started, and ever updating and ever improving. Python is proving to be a force to be reckoned with in this particular niche. So when it comes to data science and model building or machine learning, Python is always having a greater edge than R basically. And as I said earlier, other languages that support CV in particular are C++ for neural engines and JavaScript. By JavaScript, I basically mean React Native, because React Native has extended its liberty to supporting TensorFlow. So basically you can do machine learning on the browser itself. So if you have a web app that wants to authenticate user based on his face, that we can do that as well. So React Native is proving to be a good deal when it comes to browsing here as well. To approach a CV engineering problem. So yeah, as I said in my first point here, this can get very tricky and people get confused when it comes to solving computer vision problems. So there are two types of deployments that exist when it comes to deploying CV solution, and these are at the high level. One would be a hardware approach, which can be on-premise, just like our Tesla cars, and another would be the hybrid or a cloud backend approach. So first of all, before tackling any computer vision problem, we need a vision sensor or a camera basically, and picking the right sensor is definitely key, and it will either make or break the solution. So if it requires an onboard sensor, that is if the use case we are dealing with, let's take the example of a car, and the car doesn't have a camera. We need a camera that is on board, right? That is on board either on the dash or on the bumper or any generally accepted places. Okay, so such as a car, we need a very resilient sensor, right? And if you are processing this data entry in the back office tasks, which I talked earlier, such as invoice creation, order updation, and other tasks, we might need the documents we are processing with as minimal changes as possible to ensure a higher amount of accuracy. I'm not saying that we won't be able to do documents that are very different from each other. We need to have better training examples accordingly based on the variation in the documents we receive. And we should also develop ways to efficiently power up the sensor in case of an outdoor use case. And also we should be able to keep track of the sensor without it turning out to be a man out in the field alone, without a two-way communication with our service. And with the above discussions in mind, let us see some of the challenges that are usually associated with CV engineering problems. So in case of hardware warehouse management use case, right, we are seeing and analyzing gaps in the package stacking, or we are checking if there's crevices or marks in the dimensions of the box, if the box is not of the right dimension, or it has some, default, some kind of marks on it. And when it comes on the conveyor belt for sizing, we need to be skeptical of three things basically. One is being our sensor position, our camera position. The other thing being the indoor and the outdoor lighting, and the environment factor. So when it comes to the conveyor belt use case, there camera position needs to be key, right? So you place the camera somewhere, it should be able to see all those packages that are coming in, right? And it should be able to analyze based upon the initial survey, and it should have a better image recognition, and it should also have better retention. You cannot intentionally slow your conveyor belt just for the camera to pick up the item. The camera should be as fast as time wants it to be, right? So that is how it should be positioned. And that is quite a difficulty when it comes to, when you don't have a camera that has good frames. By good frames I mean, like 60 frames, not anything less than 40 frames, because there will be a time delay in recognition, and it won't be as much an efficient solution as keeping a man there instead of the camera. And when it comes to onboard cameras as well, such as the front facing bumper cameras on cars, the camera should be impervious to both the lighting and the environment factors, so it should not be susceptible to the environment and get worn down over time, right? And for an onboard camera on a car or a truck, the image sensor should not be affected by lighting, so it should be able to pick up whether it is day or night. It should be able to provide a smooth passage of the vehicle. Also, the camera unit should be incorporated on its respective position on a good vantage point, either in the bumper or the dash, and it should be impervious to the environment, without it being susceptible to damage of its sensors. And when it comes to software use cases, like the ones I said earlier, the only requirement is that we need a deluge of data, right? We need variation in the data. We need a lot of examples for true positives. We need a lot of examples for false positives. And the model should be capable of discernment on the data that it has not seen before as well, which is basically ensuring good accuracy on data which is not being used in training, right? So thus far, these are the common difficulties that arise when tackling a CV problem, and the high level solutions are discussed here as well. So moving on, if we take up an image classifying use case where we have to make sure to segregate all possible training samples in two labels, which is true positives and true negatives. And as a measure for extra caution, we would also have to batch segregate those images that can be of different textures or color. What I mean by this is, if we are building a mask detection model where the model returns either 1 or 0, 1 if the person is wearing a mask, and 0 if the person is not wearing a mask. And we have painfully struggled and collected, and we have visited many websites. We've gone to Google, we've gone to Tumblr, we've gone to Pinterest to find our training images, and we have got a list of 1,000 images with people mask on in the hospital, and most of the people seem to be wearing white as a predominant color. Let's just assume they are wearing PPE kits, right? And around 750, and the others are wearing blue as a predominant color. And we have another 1,000 sets of images with the same ratio who are not wearing masks. Let's just assume this is the case. If we do not batch these images currently with equal percentages of white and blue, I'm sorry, there's green there, white and blue, there will be a major problem when it comes to accuracy. What I mean by that is, if there is a lot of variation in your training data, then when the model tries to understand the use case there, which is the images there, If you don't segregate like in these percentage, I'm just taking this as an assumption. So it is basically, you have to get dirty with this, right? You have to change the percentages to see if your accuracy increases. So let's just say we give a batch of 10 images at one time, and in those 10 images, 8 images are white, one image is blue, and one image is a false positive, right? This is not a ideal batch, but yet still I'm taking this case. And if you do this unanimously towards all the batches to the images, 2000 to all 2000 images, if you batch it like this, you should get around 200 batches, right? You provide a batch training of 200 here. So if you do it in this fashion, you secure a spot of good accuracy. Otherwise, if one batch contains all white and with only true positives, and another batch contains all blue with half true positives and half true negatives, your model is going to get confused basically. So thus far, this will be the common difficulties that arise when tackling a CV problem, both in terms of hardware and in terms of software. Yes, so moving on, these are the frameworks or packages I use in Python on a daily basis when I get involved in CV problems. One would be being scikit image, and the other being PyTorch from Facebook, Matplotlib for plotting my images, and Google Tesseract OCR. OCR is basically called optical character recognition. There is a slide following on this also. OpenCV is yet another image handling library, Keras and TensorFlow. So some of the hardware problems I've used, the sensors I've used are NVIDIA Jetson, Intel RealSense camera, which is able to pick up even the slightest details. It is very good. And last but not the least, everybody's favorite Raspberry Pi, which is a tiny computer that can be coupled with any type of other sensors to give it that edge. Basically, it is basically customizable. So before moving on to the algorithms discussed, I would like to give you a small intro to neural networks. So neural networks is a series of algorithms that try to recognize the underlying relationships in a set of data, basically. And the process is the same as how our brains try to understand these, right? So in a sense, neural networks refer to the system of neurons, either organic or artificial in nature, organic being us and artificial being this. Neural networks can adapt to changing input. So the network generates the best possible result, the best possible weight based upon the input it has been given without needing to redesign the output criteria. So that is the kind of the edge neural networks have over these generic statistical models being logistic regression or whatnot. So that is why usually people opt for neural networks, and that is why neural networks are generally considered when we go for a computer vision problem. And neural nets are also a means of doing machine learning in which a computer learns to perform some task by analyzing training examples. Usually these examples have been hand labeled. So when you get all these images, right, just like the last use case of the doctor's use case, you get all this information from the internet, but it is not ready to be fed inside the model. You'll have to label each and every images such that you basically draw a box around the object you want to identify there, right? So if you see a doctor with his mask on in white, you just draw a box around there, and the box basically defines the pixel position from the top left to the bottom right. So it basically covers an area of a rectangle or a square, and that is what the model uses to get itself trained. So that is what happens there. An object recognition system, for instance, might be fed thousands of labeled images of cars, houses, coffee cups, and so on. And it would find visual patterns in the image that consistently correlate with particular labels. And here's the funny thing about neural networks. Nobody can give a proper definition as to, we know that it is governed by weights, right? We know it is there's feed forward networks, we know there is back propagation that happens on a regular basis in a neural network. but not everyone is able to, including me, not everyone is able to, have a proper idea of what exactly happens on each epoch in the hidden layer. So people are actually afraid that neural nets might get smarter than we think it is. So that is a funny theory that is going around right now in the data science world. So coming back to our topic, since CV is a very repetitive process, right? So you use it on a regular basis, right? You want it to be there, alert all the time, watching, right? And it needs and it will need constant updation if it is performing not very well. Constant updation, and it is not the gradient descent of logical logistic regression is not equal to the back propagation when it comes to a neural network. Okay, so imagine a case here: we have trained a model to identify people without a mask. So based on the collection of input data, we hosted a regressional model on the cloud into an embedded camera on a certain vantage point. The vantage point being a pole or a light stand. A street light. Sorry, as a street light that can cover a widespread area. Since it is only a binary classification algorithm, there is a high success rate. But when it comes to multiple factor detection, that is where it loses its edge slowly, one by one. And there happens to be a fault at the time. So if you have a fault at the time, no matter the amount of data you train them with, at one their accuracy it is not going to increase as and the amount of input increases, the output is not regression in place of a neural network. Then when back propagation occurs, right, the individual weights of each firing neurons is changed accordingly based on the neuron it fired to give us that output, which in turn will be added value to contributing an increase in accuracy. So whenever there's a false positive, the weight is accordingly reduced such that only our accuracy is not affected, but only the weights is affected. But in the case of logistic regression, it is not going to be the same. And this is a paper depicting a binary classification at better than logistic regression, which gave us 95% confidence level. So marginal, but in spite of, you can also refer this paper, which I've linked here once you're done with this presentation. So neural networks that enable CV. So let's get down to the actual neural networks that that aid and help in creating solutions. So there are different type of neural networks. Like there are recurrent neural networks, there is long short-term memory neural networks, and when it comes to computer vision problems, it is convolutional neural networks. So basically, we use convolutional networks as a base for everything. We use a base for everything, and upon that convolutional neural network architecture, we start building our other approaches. So a typical use case for CNN is where you feed the network images and the network classifies the data, right? You feed the image of a dog, it says it is a dog. And CSS tend to start with an input scanner layer, which isn't intended to parse all the training data at once. Let me explain this in this way. So a CNN neural network basically can will be the convolutional layer. Third will be the fully connected layer. Fourth will be the softmax or the logistic regression layer. And fifth will be the output layer. So basically, any CV comes with these mandatory 5 layers. A basic representation of a neural network, like the particular image I showed you back here. 1 second. If you could see this particular neural network, this is a generalized neural network which has one input layer, one hidden layer, and one output layer, right? So a CNN has all these 5 layers. CNN looks at an image, right? So before moving on to that, let me just tell you the other types of CNN there as well, and then I'll start explaining about the images. So there are many variations that are built on top of the CNN. One being RCNN, regional-based convolutional neural network, that concentrates on regions of interest within the image. So it has a selective algorithm that searches for regions of interest and takes it into particular account to identify features that we are trying to use to train the model. This uses a selective algorithm to pick those regions. The other one being faster RCNN architecture. The faster RCNN architecture is even more delicate and even more faster than an RCNN architecture. This works on the same principle as RCNN basically, but it includes another extra layer called an RPN, a region proposal network. RCNN uses a general selective algorithm to find the regions. It uses a separate network of neurons to find that regions based on the input. So that is why RCNN is a better and even more secure model when it comes to identifying or classifying images. So I just take a bit to give you a better depth of understanding. If you use a basic CNN model, you will be very well be able to classify images such as if it is a cat, if it is a dog, and you can also use it to detect multiple objects. So there can be a cat and dog in the same image. You can use it to design if there's a cat and dog within the image. And when it comes to RCNN and faster RCNN, there's one slight edge. So remember how I told you that during that technical exhibition, our ID cards had different designs, had different fonts. You can identify the semantics or the design, the actual design of the image, such that you can identify if there's a table in that particular image. You can find that paragraph and label that paragraph and do it. It would work based on the template of the image we are feeding, not the pixels we are feeding. So that is why people usually go for, or even me, when we have to build a custom model, right? When we have to build a custom model for a set of invoices, like let's take 700 invoices. So we go for the RCNN or the faster RCNN approach. Forward, let's just discuss one deep learning based CNN architecture there. So yeah, before getting this, I'll just explain how the CNN works. So you have an image, right? You do not feed the image directly. You break it down into pixels. So let's just assume the image is 28 cross 28 pixels. So at total 28 cross 28 is 784, right? So you make it into one-dimensional matrix basically. You feed it into the neurons. That is how you depict the idea of that is how you find the number of neurons that is supposed to be in the input layer. So you feed it to those. What it does is it feeds it to the convolutional layer, where a convolutional layer, let's just say we picked up three particular pixels there, right? If you can see the image on the bird, there's a small square. That small square is convoluted again and again. So if it was a 3 cross 3 pixel, it would be again multiplied with 32 into 3 pixels to expand its space. Okay, basically expand its space and give it more depth, more regions to classify. Zoom in, zoom in, zoom in. Basically, that is what happens. It basically zooms in to the core on the convolutional network. Then it goes to a max pooling, which is basically a filter you provide there. A filter which limits the number of pixel input you give into the hidden layer. So that is what you use max pooling for, to limit the number of pixel layers If you give it a very low amount, the training usually takes a lot of time because you're feeding a lot of images, because it increases on the powers you feed it, right? Feed power 3 to the power 3 like that, right? So that is what happens, and it will go on to the fully connected layer, which is the third layer, and moving on, it will go on to the softmax layer or the logistic regression layer, which basically classifies the image, and from that layer it goes on to the output layer, saying if it is a bird, if it is a cat, or if it's a dog. So that is how basically a scene and architecture works on a high level. And first and foremost, the thing we need to develop a computer vision model is getting our data. And this is, trust me, this is actually the most difficult part of the entire pipeline. People, usually web scroll for nearly million websites to find suitable images that can be used in the training. Then comes the data cleaning. So if you don't have a valid data based on your web scraping results, then you're not going to, or probably going to use that image in your training, right? And you update the data. By update, I mean basically label the data. If it is fit for using in training, you label it. And enhancing the data if it does need any enhancing, because it can be of a lesser pixel, but it can be a good image, right? Like a good image that can facilitate in the training, so you can enhance it as well, and then use it for training. And then comes the data cleaning part. Once the steps are done, we will have to segregate those data into true positives and true negatives, such that they're used for training once they are appropriately labeled. So mask on, mask off. Once they are labeled, we need to figure out the percentage of true positives present in the image. Since CNNs are convoluted, this will play a huge role. Also, when selecting layers, we need to make sure that there isn't much difference between the image. So basically what I'm trying to lots of variation, you are going to end up with a model that only identifies the images that you trained it with, not the images that are new to the model. So it will have a difficult time actually finding those. That is what happens there. So moving on, we also have to make sure that the images that we are using should be of the same size. So this is all different sizes. You cannot use one image of 28 cross 28 pixels and another image being 50 cross 50. You're using. So CNNs are usually fine because higher the pixel density, higher your attribution to accuracy, right? So get our 3-layer setup or the softmax layer. Finally comes the output layer. So the number of neurons for the input layer is based on the image size basically. So assume that we have an image of 28 cross 28 pixels. It is going to be 784 pixels in total. So just like I said before, you convert it into a matrix, single dimensional matrix, and therefore we have a first layer. So you have something called as a feature map, which is depicted by L, which connects with the input features. So if an image has L, it is considered as input, and if an image has K, it is considered as output. So that is what you find in the convolution layer. So you can play around with this. It doesn't necessarily have to be a 3 or 2 or 1. So it is not like that. Based on the types of images you're using to get your output. The fully connected layer will use the same parameters used in the convoluted layer to calculate their parameters as well, which is equal to L plus 1 cross K. And the output layer parameters can be calculated as follows, okay, which is input size of the pixels in the image minus the filter size minus 1. The input size will be 50 cross 50 image, and the filter size will be equal to the set of LK. So we found this LK, and if we have L to be 3 and K to be 3, we use 1. So we use 3 here. We found in the convolution layer. With these basic configurations done, we can test out a neural network by starting to train them. In Python, there are already packages that come with the standard architecture that we can just play around with this, change those, and see if the results are any better. So we do not have to worry about building an architecture, because there are a lot of examples for it. We just have to know how to change the architecture accordingly, so that we are not affecting our output. That is what you have to make sure of. So before moving on, I'll just explain my projects I've done on OpenCV. OpenCV, as in the computer vision projects, and I've done various projects during my free time, and while I was in college as well. And two of them being what we called military-based tactical Land Rover, and the K-Site app, which you will see a demo of in the coming slides. So Land Rovers, right? So basically, if you can imagine, that is a Land Rover. What we've done is we added all-terrain system setup that runs on a bed. Basically, it is a mini tank. So it is like a small tank that houses ultrasonic sensor, thermo imaging sensor, 3.5 HD camera for Raspberry Pi, compatible with Raspberry Pi. I believe it was around 1.2 aperture, and we had a Raspberry Pi on board. Obviously, we had some motors to drive the chain train. And what particularly is interesting about this Land Rover is that the algorithm which we used, we did get some help before doing this. Since our idea was good, what we did was we readied up a database of entries, right? So let's just say we are in India, and we are trying to deploy this this rover in war. So we're fighting some other country, we're trying to deploy it on the border side. So it should be undetected, right? So based on the terrain, it should be adaptable there as well. So it should not be hindered if it is not able to move up on a slopey terrain, or if it is stuck somewhere or whatnot, right? So what we did was we got readied up based on the terrains and based on the people. How is that? We took training data from Google Maps API. Okay, based on the location, it will know that if the terrain is suitable, or how manageable it is for the for the rover to do. And for identifying enemy personnel, we just did not use their uniforms to identify if they're enemy soldier or whatnot. We took in major factors. Okay, one being, if their face is not being able to recognize. The other being, if they are wearing the enemy colors, and the third being weaponry. So we did not get access to lots of images by hand. We had to use our backup, which is being miniature guns, and we use that with the small toy sitting, man-like toy sitting. So it doesn't know the difference that much. So that algorithm was a good algorithm, and we got good recognition for it as well. And the K-Site app is what I've been saying for a long time. So what it basically does is, what I basically done is, it was my side project, and what I did was, I took a set of invoices, and I recently studied that I can use YOLO V3, this CNN architecture that can be used for identifying this. Not necessarily semantic, it is not necessarily working based on the templates. I just wanted to see how accurate a model working on colors and pixels would be when compared to a faster RCNN model, because there was already a guy who had done this using TensorFlow, and it was an RCNN model, and he identified templates and not colors. But this particular model worked on colors. So what I did was, I took around I believe it was around 250 or 500 images, and it took me a week to only collect all these images, and I had to go through all the processes which I said earlier, clean them, order them, stack them, update them, enhance them, and whatnot. And I fed it to this YOLO V3 darknet, which took around 2 days to completely train because my graphics processing unit is not that good. It's only an NVIDIA 1050. But if you want to have like good processing equipment, or you don't have good processing equipment and you want to loan from somewhere, you can use Google Colab basically. So if you use Google Colab, you get a very good system with a good configuration, and you get the latest TI based NVIDIA graphics, which is faster, it's much faster. But it is only available for you for 12 hours, so be sure to save your output data or your weights when you are running your models on Colab. You can save your weights to Google Drive basically. So I based it on colors, so it got trained, and I used 10 out of the images, 200 images that I did not train. I did not train the model with that, so it was able to identify good basically. But I did not know back then that if I use too much variation in my images, it will be posing a problem for me. So I used templates which are completely blue, which are completely white, which are completely red, and it was disproportionate the number of invoices of color that I used. And for most, not like for most, I would say around 20% of new images that were kind of hazy or kind of extraordinarily new, out of the box new, out of the ordinary new. It was not able to identify the table color. So I came to the conclusion that I did something wrong, but basically what was wrong was the disproportionate of input images. So one thing in this particular case, I needed that extra, needed that extra input data, but you can achieve very good amounts of accuracy. I'm talking about over 90%, 95%, just by being, just by collecting very meager amount of data but training your model properly. So OCR, what is OCR? So I told you before that it is called optical character recognition, right? So basically what the guy at the technical exhibition did was he used a solution that was on one end it had computer vision, one end it had OCR, right? So based on what he did that day, I'm assuming he had trained a model to see if there's labels within the image being our ID cards. So what basic information does our ID card own? Our ID card in the front face, I'm just talking about the front. It will have the grade we are studying in. Basically, it will have a name, it will have a picture, it will have a barcode. If some colleges have that, they have a barcode there as well. And my ID card had this transport thing. So if I were using my school bus, if I were a private student, or if I was in the hospital, so was able to beautifully identify all those. So that is a mixture of OCR and computer vision. What computer vision did there was put boxes around the photo, my name, my classes, and the type of transport I use, and the other being the optical character recognition being identifying text from that image. So once the boxes were put around my ID card, OCR, basically what OCR does is it optically recognizes the character within that image, within that bounding box, and tries to extract all that images. Okay, so it can work on text, symbols, and numbers. So one of the best OCR engines we have currently out there is from Google called Tesseract OCR. And since I'm an RPA developer, this comes in handy as I deal with a lot of images when developing bots on a daily basis. Bots, in this case, being RPA bots, robotic process automation bots. The same conditions apply here too when the images need to be of high quality, based on which the accuracy might shift. Sometimes the OCR engine reads the small letter E as I There can be instances of that, but if you use an image or a PDF or a document with good accuracy, I mean good pixel density, get good accuracy on the OCR as well. So the demo which I promised to show you will be a sandwich of OCR, CNN, and JavaScript, where I can dynamically which I explained earlier. JavaScript converted as a desktop app basically. So I've used Electron Days to create a desktop app. I've coupled it with Python. I had my model on Colab and I exposed the APIs. And whenever I fed an image, it will pick that model, get the results back, and feed it here. That is what happens in this own process. Some of the free OCR engines out there being Tesseract OCR, Amazon Tech Stack, and OpenCV, of course. So techniques we use. The final thing, the basic purpose of using computer vision. So there are basically three things. One being image classification, other being object detection, and the other being image segmentation. So image classification is self-explanatory basically. You give the model an image, ask it if it is a dog or is it a cat, and it returns stating that it either found a dog, a cat, or it did not find anything, right? What is object detection like? What if there are multiple subjects in the image and you want to separate those subjects and see which pixels perfectly depict that subject? So that is what you're seeing in the second image there. You see an yellow bounding box around the cat and a red bounding box around the puppy, right? The kitten and the puppy. So that is what object detection does. It is able to identify within the image some subjects which you have trained earlier. It will not be able to classify it. It will be able to identify the subjects within the image. So you would have to add another classification algorithm there just to give it a label if it is a cat or if it is a dog. So that is what object detection does basically. And image segmentation. One of many use cases that corporates use even now. This basically gets used during the onboarding processes. Let me elaborate on that later. So what image segmentation does is a combination of both basically. So to know that if it is a cat or dog, to know where which pixels that depict the best best subject based on the availability on the picture. And what image segmentation does is it will try to identify only the pixels that are concerned within the bounding box. You see the bounding box on object detection, you can see that there is a lot of pixels which depict the background there also. Some depict the grass around the puppy and some depict the foliage, I mean the dark trees behind the puppy, right? So image segmentation will try to cut out or identify only the subject within the image. So a general use case for this being would be faster onboarding processes. So basically any company when you're joining for the first time, they'll ask you for an image, right? So people sometimes they post selfies, they post their passport, their good passport photo, or they have a good professional, headshot, profile shots and whatnot. So the images are going to differ based on backgrounds, based on lighting, and based on everything, right? So what big tech giants usually do is they enable an image segmentation algorithm to, carve out the person and put their image on an ID card. This is just one of the many use cases that when it comes to image segmentation and corporates, but I'm just taking this for the time being now. So moving on, how RPA and neural nets go hand in hand. I've explained this multiple times. I'll just be brief. So RPA bot sits on his desk 8 hours a day, entering only the details from an invoice he receives throughout the day. This is basically what an RPA does, but at an even more faster pace. So let's just assume that guy takes around 20 minutes to post one invoice inside his ERP. By ERP, I mean its enterprise resource planning system. It takes around 20 minutes to fetch that invoice from his email, download it, open it, see take it for cross reference. And if the ERP is programmed to accept CSV files, it is even more tedious. He has to copy paste each and every image based on some particular template and then upload that CSV. So it takes more time. Let's just assume this entire process takes around 20 minutes for the guy, and he usually processes around 100 to 200 invoices daily. And this is his only job. He is not doing anything else. He is only posting invoices in a company. And if you take it to scale, this would be a mandatory case because huge companies, big tech giants or big retailers receive lots of invoices throughout the day. So they do need dedicated personnel doing this on a daily basis. So that this is where RPA pitches in basically. So RPA can help by not by replacing the guy, he relieves him of his work so that the guy can be used on a better value adding task basically. So the RPA will take all these invoices and with the help of computer vision and OCR. So basically, if they want a low price solution, if the customer is looking at a very low price solution, the client is looking at a very low price solution, we usually go for an OCR approach, which is regional based. So we take this particular template, feed it to the model, and we ourselves draw these boxes around the image copies so that it will know that it has to identify this particular regions in this particular template and hand over the extracted text to us. So once the text is written to us, it can be either in a JSON format or we usually return it in a CSV format. And if the as I said earlier, if the ERP is programmed to accept CSV files, then it can easily post this. And this entire process from reading the image to posting can be done within 5 minutes for the bot because the bot works on an operate the OS level. It sits on top of the OS, so basically it is faster in navigating in mouse clicks and button clicks and whatnot. So when you take this, if the guy's salary is around, let's just say his salary is around $10 a day for doing this, on a monthly basis it's going to be $300, and on a yearly basis it's going to be $3,600, right? So you can basically take resources that are not doing any value-added tasks such as these, monotonous tasks such as these, and replace it with RPA. So that is where RPA and neural nets usually go hand in hand. So moving on, I just show you the demo I So the demo I'll be showing you is the invoice demo which I told you earlier, the custom app picking up or not. Sorry, I should have got this ready earlier, but please bear with me. So meanwhile, if you have any queries or questions regarding I hope everybody can see this video. I was not displaying. This is the custom app which I developed, and if you see, is that I did not train the model with invoices. I did not train the model with. So as you can see, so I was done with the being said, hello all. I hope it should be done by now. I'm sorry, I was not responding to your messages back there. I was just walking around while I was talking to you. Is it okay now? Or you could just post your queries in the discussion.
It's okay. It's okay now. Now it's audible. Yeah.
Yeah. So if you want, you can just I'm sorry, I've connected through my mobile here. Is it okay now? I was just saying, if you had lost me in the middle, I'd be happy to represent the slide there. But if you have any queries, if you can't able to reach me, can you just post your queries on the chat? I'll be happy to answer them. Yeah, thanks for understanding, guys. I'm really sorry. I seem to be having an internet connection fault at my end. Please post your queries on the chat so that I'll be happy to answer your queries. Please, people. Yeah. Okay. Yes. I'll just I'll just verbally explain on how to show you the how to calculate the neurons once again. And Dr. Sony, I'll be happy to share you the demo once again. Dr. Sony, please hold on. I'll be sharing my screen from my mobile here. Uh, to to roll back towards the calculating the number of neurons. So basically, there's five layers, as I said earlier, right? You have an input layer, you have the convolutional layer, you have the fully connected layer, the softmax layer or the logistic layer where the actual classification occurs, and the final output layer. So when it comes to input layers, you have to think about the size you are using for the image which you are going to train. So if the image is of 28 cross 28 pixels, then you'll have to use you have to multiply those pixels basically. So 28 cross 28 is around 784, and the 784 is in the form of a matrix, right? You have to convert it into a one dimensional matrix. So it was earlier a 28 cross 28 matrix. You have to convert it into a 784 cross 1 matrix. So that will be the number of neurons that will be in the input slide. And moving on, we will have the convolutional side. The convolutional side will have two factors. Okay, the layer will have two factors. One being termed as L, which will be the input feature map. Okay, which is called the input feature map. If the layer is able to find this input feature map, it will label it. It will take it as L, and it will identify it as an input. And if the input feature map has K, which is the output, label it as K, and we'll take it as output feature map. Okay, so you'll in the end you'll have a set of L comma K, which is called the feature map set. And you this is just an arbitrary value. You'll be the one who will be playing around this value. So yeah, you will have to play around the value to get your desired output in terms of accuracy. And then comes the fully connected layer. And where there you how you find the number of neurons there is basically you use these two factors which you used earlier, which is L and K, which will be L plus 1 cross K. So you'll use it to calculate the number of feature parameters in the convolutional layer. And as an added extra bit, right, you can use the same number of neurons in different layers. I mean, in different numbers of layers in both convolutional and the fully connected layer. Once the fully connected layer is done, you will have to hand it over to the softmax layer, which should have the number of neurons equal to the output layer. So let me tell you how to calculate the number of neurons in the output layer so that you'll have an idea. So the number of neurons on an output layer will be equal to input size minus bracket filter size minus 1 closing brackets. So input size is the size of the image basically. So if it is a 50 cross 50 image, it will be 50. The input size is 50.
minus the filter size, right? So LNK. Since LNK is always the same, you'll use that particular number, in place of the filter size. So you use 3 if you have the set of LNK as 3 comma 3, so you use 3 there. So that is how you calculate the the neuron count on individual layers. So I'll just move on towards Dr. Sony's request, where he asked me to share me the demo. Pardon me, sir. I'm just sharing the demo from my screen. Please hold on. Yes. I hope my screen is live, and I'll just wait for it to load completely. Yes, I think I'm sharing my screen, so I'm just heading over to my LinkedIn to show it to you. Yes, uh, I hope you can see the demo here. One second, let me shift it. Yes, this is the custom map which I developed using the technologies which I mentioned earlier. I have a set of images here. If you can see, these are the images that I did not use to train the model basically. And if you're considering to use it as the input images, you should not basically, because if you see, this is what I've been talking about for the whole presentation, which is you can see the variation in the invoices, and they are disproportionate, right? You can see there's a lot of blues, there's a lot of whites, there's a small hints of colors in both, and there's red, and there's completely bland white. So you should not use this as an input set. To just check the feasibility of my model on how well it is trained, I used it as a good indicator to know that the model has been trained properly. So I'm just selecting the first image, just posting it here. When I hit on predict, it will go and ping the server in which my model is hosted, and the model will return the areas in which it has found. So basically, what I've identified in these invoices is the vendor details, which will be the top box, and the invoice details, which would be the table that comes in all invoices, right? So I've only taken all examples that are tabled invoices. There are also invoices that don't come with tables. So we can see clearly it has predicted the model at around 99 percentage for both, including a table. So just feel free to navigate to the profile, and you can see it slowly, and you can discern whether how it has done. So as I said earlier, this model is not based on semantics, which is, it is not based on templates basically. So it is only working on colors. So it is a basic CNN model called YOLO V3, and for a model that is working only based on pixels, it has done very well, is what I would say. So this will be the demo, guys, and if you have any further queries, you can just uh, ping me on LinkedIn, or you can just shoot them here itself. Yeah. Uh, Hello all. If you don't have any further queries, shall I know it in the in-call messages, please? Really sorry for the delay in my voice, or if you weren't able to see the presentation, guys. I worked very hard on the presentation to give you a good one, but unfortunately, I've been facing these issues over here. So if you found something to be very ambiguous, or you were not able to catch on pretty quick, please feel free to message me on LinkedIn, and I'll be happy to answer all your queries. If that is all, then I'll just take leave from the call, everyone. So I have this meeting coming up for me, and it is almost 11 o'clock. I thank you for being the patient crowd you are, and thank you for putting up with me. I hope you found the information useful here. And thank you for coming, guys. Thank you for making my day. Yeah. And thank you for coming. Thank you for.
And thank you, sir, for your thought provoking session. It was highly informative. Thank you, participants, for the session. Next session starts by 11:30. Wish you all happy learning.
Already, ma'am, stop the recording, ma'am.